Well, good morning, everybody. Today we're going to talk a little about the lightning protection systems as well as tree support. So again, if you have questions, please drop them there in the Q&A section, or if you think about something afterwards, you're always welcome to email me directly. So let's go ahead and get started. So we're going to talk about the benefit of cables, guides, bracing rods, and props. We're going to talk about the limitations of cabling and bracing, both physically and from a perspective of mitigation. Methods of providing supplemental support. There's several different types. The techniques and materials used in cabling and bracing. We'll talk about the arborist responsibility, the benefits of lightning protection systems, and the techniques and materials used in lightning protection systems. Some of this can be pretty difficult to get the right imagery in your head. So I encourage those that have never worked with a tree company or for a tree company, go out and find yourself a mentor, a company that you can shadow for a little while. Ask them if they do lightning protection or cabling and pruning for that matter. It's important to be able to see the techniques that go into play. And there's just something about being there in real time and seeing it being installed that helps you to fully envision the things that we're going to talk about today. You know, this exam is meant for you to have practiced arboriculture for a year or two before or longer before you take the exam. That means every facet of the exam, all the different chapters. So it's important to be able to immerse yourself into all of it. Whatever you think your weakest link is. I know some of you might be climbers and this is super easy, and some of you might be government employees who are administering ordinance type things, and you might never have seen a lot of these things that we'll talk about today in action. So given that information, let's go ahead and move on. So what are we trying to do when we're supporting a tree? So junctions between codominant stems are considered the weakest portion of the tree. You know, what does codominant mean? So these are the two leads of a tree that are about equal in diameter. There's not going to be a branch collar. There's really not going to be a branch bark ridge because there's no collar to develop that ridge. You might just see that seam where the two bifurcate. So each one of those is referred to as codominant. Each is its own entity, so they're codominant because of their size and a lack of branch collar. So that's a very weak union. It's not a physical union. It's just held on there by the outer sides. They never really connect. So what we try to do is support that weaker crotch. If we can't prune it out or work it out quick enough, we try to support it by using these support mechanisms. Especially, like think about a Bradford pear in your head. We've all seen them. They have this profusion of branches from a relatively small area of the trunk. Each one of those branches grows in diameter or adds secondary growth at the same time. And so they begin to push on each other, push. And about the time they get around 12 years of age, they fall apart, they explode. It's still a pear. Pears can live over 100 years. So it has nothing to do with the health of the tree. It's purely a structural and genetic defect in that particular tree that causes it. That would be what we would refer to as a multi. Here we talk about codominance, which might only be one branch. Let me get my highlighter going. There we go. So, or it could be, we might want to support all those multiple stems together to get it to move in unison. We might want to prevent splits and decay, or if it already has some decay, we want to take some of the pressure off the area where the bifurcation occurs. We might also want to support very large branches, large, long branches. If you think about a lace market now, once the branches, their taper, genetically, their taper is not all that great. So we have this very long whip-like branch, get a big storm or some ice, and they tend to split off. If we can identify those beforehand, we can either cable them or prune them, or a combination of the two. The support systems cannot be thought of as eliminating a hazard. Hazard, let's keep in mind, is a legal term. Once an arborist deems a tree to be a hazard, it's always a hazard. So even installing protection systems in it we're not going to change the designation of that tree from hazard to, potential to a high potential of failure. It still remains a hazard and should be dealt with as such. However, we can reduce the risk to acceptable levels, perhaps through a combination of cabling and guying and pruning. So again, trees must also be assessed very carefully. The condition of the tree must be considered before installation. You don't want to install a system in a tree that's, you're trying to get this bifurcation to hold together, but the base of the tree is 60% gone because it's rotted away. So it's really not, the big issue is not the codominant area, but it's the base of the tree. So keep that standard. Keep that in mind. Follow standards and the ISA's best management practices, tree support systems, cabling, bracing, and guying. Keep in mind there's also an ANSI standard for this. I will get that complete set of standards. I've said this several times, but that's the primary source for a lot of the documentation that you see that's being presented in this review course. So if you can go back to that original documentation and read through it, or you might have a little better understanding and it might become a little more precise to you. So cabling in itself restricts the distance that a branch can move in relation to each other. Again, we sort of talked about this sort of codominance, and these things can on their own move in the wind like this, and it produces this very kind of chaotic action. What we don't want to have happen is to separate where that seam is being produced. We'll see some pictures of this a little later. But when you put in a cable, we want it to move like this instead of independently. You're still going to have some movement, but it'll come and sort of snap, and it won't go much further than that. Bracing. So bracing rods are used to reduce the risk of 2 or more leaders spreading apart from or moving sideways in relation to each other. So cabling happens 2/3 of the way up in the canopy, and bracing right in the area of where the bifurcation begins. Then the next thing that we'll talk about will be guying. Guying is the installation of a cable between the tree and some external anchor point. So in this case, we were talking about a cable going between these two. If you think about a guy, it's going over here to the ground somewhere. It's attached or to another tree or to a building or something, but it's external connection point that's going to limit the movement of the tree. As cable installation limits the movement of limbs with weakness. You can help support heavy limbs by connecting 2 or more of them together. Again, it's going to support multi-stem trees and protect the limbs or branches from heavy snow or winds. Again, this is just one tool. It really needs to be done in conjunction with pruning. In the picture, you can see this guy, he's getting ready to install a bracing rod through this weak crotch. This is codominant. Notice how both of these are relatively the same size. There's a seam that comes down right there. And there's no real physical connection between this side and this side because they are codominant. Remember it used to look something like this, and then this grew in secondary diameter. This grew in secondary diameter until they began to push on each other. Then over time, it produces the seam that you see. So you can see this very long drill bit that this climber has. He's going to drill all the way through this installed brace. We'll see in a moment. Cables should not be installed in trees that do not have a structurally sound root system. Again, it's important to inspect the entire tree before making the decision to install cables. But as the installer, it's also your responsibility to make sure that you've done a full risk assessment on the tree. The sales guy, he might go out there, or whoever's running the visual assessments might identify something that sticks out. Remember last time we talked about being systematic so that you don't overlook something. Don't jump straight to the obvious thing. There might be something even worse in the tree, and you need to take your time and take a look. So no need in installing them if the tree's going to fall over it anyway. Trees with decay should be considered for removal rather than cabling. Remember in the biology section, we talked about the coded model, compartmentalization of decay in trees, and we saw where some of those walls had failed and the tree had to produce another set of walls on the outside of that. So the progression of decay is inevitable. It's going to continue to decay. It's not going to be totally isolated. So if you're marginally safe to install a cable and bracing system, but it's an older tree, it's not going to grow as much in the future, you're at 30% structural strength loss, sort of the threshold's at 33%. Is it really worth installing these cables? Should we just go ahead and remove this tree and get a new one going? Before installing cables or braces in a tree, the tree should be properly pruned to remove hazard limbs and to reduce the weight of the limbs to be cabled. Again, I can't stress how important it is that all of these things should be done in conjunction with each other. So we're going to talk about some of the hardware. So we'll talk about common grade and EHS and aircraft cable or woven style cables. 7-strand common grade galvanized is easy to work with. Remember, common grade is easy to work with. It's malleable. Malleable means that it's easy to bend or to pound out. It's flexible. It's very flexible. So we can do a lot by hand when it comes to common grade cable, as compared to this EHS stuff, this extra high strength cable. From even in your hands, if you're not trying to flex it or move it, it looks just the same as the common grade. But as soon as you try to bend it, you realize in a hurry that it's a lot less flexible than common grade. And as a result, we have to use some additional connection parts to get it to become part of the overall cabling system. We'll talk about those when we get there, but just keep in mind that these are the 3 types. We've got the 7-strand. This is also 7-strand, but it's EHS compared to common. And then the next one is this aircraft cable. Think about the stuff that you might see on your bicycle, the lines on your bikes that run to your brakes. That stuff is basically aircraft cable. Might be teeny tiny, but it's aircraft cable. But they make this stuff all the way up to big honking stuff. It's very durable. It's not used very much in the United States. However, it was fairly common practice in the UK, Australia, and a few other places. It is super strong, but there's definitely limited choices for attachments because of you can't, well, you'll see in a few minutes. But another thing to keep in mind here for the test is commonly used cable size diameters are 3/16 of an inch all the way up to 3/8 of an inch. So we have, we talked about the cable. Now the cable has to attach to the tree somehow. It has to be anchored to the tree. So anchor hardware comes in either 2 types. We're either going to screw it in or we're going to push it in and bolt it on the other side. The type that goes all the way through and connects on both with a nut and a washer, this is the preferred methodology over the lag bolt. Eye bolts with an aim and eye nut, these are commonly used. It's another attachment. So here's an aim and eye, so this thing sort of screws on to this stuff. This threaded rod, you can see it here. The threaded rod comes in both a very coarse, or what they call machine thread, and then there's also a more open thread that you would use, like a lag thread that can actually be screwed in. The benefit of using this threaded rod is that you can purchase all the materials ahead of time, and then you can cut it to fit on site. So it doesn't matter if you have a 12-inch tree or you have big giant 50-inch tree or something. You can use this threaded rod to push through the hole that you're going to drill. Remember the guy that we saw drilling the hole in the side of the tree. So you'll pass this through, and then you can screw this on one end, bolt it on the other end, and then cut off the extra. The aim and eye comes in handy because it's very adjustable. The eye bolt does the same sort of thing, except it's permanently attached to the end of the threaded rod. So it takes away some of your installation flexibility. This is a really strong connection. So this is just as strong, but you can see it's much larger to get the same sort of strength as the eye bolt. I mentioned earlier that there's two ways. You can either go all the way through the tree or you can just screw it into the tree. If it goes all the way through, it's got this very hard to think of name, through hardware. So meaning that it's going to go through the tree. So anytime you go all the way through the tree, you want that piece of all thread, that threaded rod, to be able to slide all the way through the hole that you drill. In order for it to slide through the hole has to be what? Bigger than the piece of threaded rod. So how much bigger? 1/16 to 1/8 inch larger than the diameter of the rod. So just think that the hole that you drill has to be a little bigger so that it slides through that hole. The eye bolt or threaded rod is installed with a round washer and nut on the end. It's important to think of this round washer. We used to use these sort of diamond-shaped washers like this, thinking that those would close over or would develop reaction wood or wound wood around that in a better fashion than the round one does. However, years and years of research have showed us that the round washers produce less. And then after you put the washer on, then you're going to put the nut on the end of it. The washer should be seated against the bark. Thick bark should be chiseled away. If you're installing these on a beech or a maple where the bark, you really don't need to do anything with the bark. Just get the washer onto the bark. However, if you're doing something like a cottonwood and it has some really thick bark as it matures, you're going to want to chisel that down, maybe not all the way to the phloem, but you're going to want to get pretty close in there. And then you'll seat that. You want the object just to try to get it to sit flat. So getting it up against as close to the trunk as you can is best. And when you're tightening that thing up, you don't want it so tight that you start crushing the tissue. You don't want to see water exuding around the edges of your washer as you're tightening it up. You want to get it just. The other type we refer to dead end hardware. So again, this is through hardware. It's going to go all the way through the tree. Dead end hardware is going to screw into the tree. We typically use this on smaller diameter trunks and branches, less than 10 inches in diameter. What you see pictured are lag hooks. There are a right-handed and left-handed lag hooks. I'll explain why in just a second. These are threaded closed-eye anchors. These are J hooks. They also make these that are just totally round, like you saw in the other ones, so that it's already closed. They come in both right hand and left hand because when you install it into the tree, the cable is twisted. That 7-strand cable has a twist to it. And so if I install these lags into the tree and I want to tighten the whole system, I need it to go in the same direction. So if I'm doing it in the same direction and we have both a left hand and right hand, it's going to tighten, it's going to screw into the tree. And so it's going to tighten without changing the twist on the cable because we're going in the same direction. So we're not untwisting the cable by tightening. You also want to seat the full length of the threads into the sound wood. So you're gonna screw these legs in to the trunk as far as you can without doing additional damage. You can see that because of this J hook, so this would be a J hook, he's screwing this thing into place. We don't want to get it so tight that this part of the lag begins to bite into the bark. We want the J hook to be just close to the bark, but not into the bark. So every turn that piece gets a little closer. Once you get to the final turn, you want them to be straight up and down like you see here. You don't want them horizontal. So these things are pretty big in diameter. So we don't want to just screw them into the tree because then it would split the bark open. So we have to drill a hole to get those to go into place. But this time we do want it to bite into the wood because we're actually screwing it in. So instead of being 1/16 to 1/8 inch larger than the hole, Now we want it to be 1/16 to 1/8 inch smaller than the hole so that the lag bites as it goes in. The lag should be screwed into the tree. So again, as the J loop ends up vertical, we want it like this, not like this. Avoid injuring that bark. Again, this works well on small trees or branches no larger than 8 to 10 inches. Here's some examples of these washers. Notice the sort of yellow color of it or golden color. These are typically grade 8 bolts. These things are pretty strong, and the grade 8 material will typically have this sort of color to it. So that's what we mean by heavy duty, even though it won't spec out grade 8 in the ANSI standard, it will just call it heavy duty, but just know that it's not a common washer. Thimbles are used to protect cables from excessive wear and affecting the bend radius. So if I have my pen and I have a little piece of cable, if I'm go like that, this area that you see on this side, that's the bend radius. So if I have something that can hold this cable from getting any smaller like that, if this permanently creates a bend radius, then I'm not going to pinch it off. And so that's what these are. These are called thimbles. And this would be the bend radius. This would be how it would, I just demonstrate going around my pen. So it's going to hold it open and keep the cable from getting any tighter than that. This thing is a quick wrap or a dead end grip. Remember I said with the EHS is that it's very difficult to work by hand. So we have to use some additional devices to get it to connect. So this is that additional device. This is the dead end grip. Inside of the dead end grip, notice we have our thimble there to help support that open bend radius. The larger that radius, the stronger the tensile strength, the closer to maximum tensile strength we can get. So the smaller that bend radius, it decreases the capacity of the cable. And once you kink it with a permanent bend in it, it's greatly reduced in its capacity. So these these thimbles help hold that open and retain the strength of the cable. But these wrap around the cable. You might have seen them laying around and just didn't know what they were, that they're sort of open like this. You lay the cable in and then you twist one of these ends around the cable, insert your thimble, and then you start to twist the other one around and it actually closes. So it's not showing it close here, but once you wrap it up, you won't see any gaps. It'll just look like an extension of the cable, just look like a fatter piece of the cable. So when we're installing these things, we want the cable to be taut. We don't want it to be slack. Trust me, this cable weighs a lot. So when you're up there in the tree, you can pull with all your might, and the cable, from branch to branch is still going to have this sort of U shape in it. We need to get some additional purchase, some mechanical advantage to keep that cable taut, where it's more of a straight line going from branch to branch. To do that, we might use a device called a come along. So this part might be attached to the tree, and this part might be attached to a cable grip. This would be a cable grip. And then we would use this long lever arm and a ratchet and the cable in here, so that as we move it, it's going like click, 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 moving it onto this drum. And as we do that, it tightens that cable and takes that U shape out of it. The cable grip is used to grab onto the cable. It's sort of a cam lock. You can see how this is curved. So the cable would run through here. This end would be connected out here to this little snap. And so when we pull on this ring, you can see that pulls. It's going to rotate around that point, and then this will grip onto the cable. It sort of pinches down on the cable as it gets tighter. So I can put that anywhere along the cable. So it's a very useful device for helping to tension the whole system. Those lags that we saw screwing into the tree, the more you get into the tree, the harder and harder it becomes to get it screwed in. So we use this device called a cable lead. This little point slips through that opening or the eye, and this little bulge catches on the actual hardware, and you just sort of screw it in. So that's a very handy tool. When we drill these holes, we want to do as little damage as possible to the cambium. We want a good clean cut as it passes through the cambial layers. So we use a type of drill bit referred to as a ship auger. These are fairly low speed drill bits. Notice how open this is. It doesn't look like a regular kind of drill bit. If you were to hold this in your hand and look at it, the leading edge on this drill bit would look very much like a knife. It cuts a very smooth hole, a very low speed hole. The sawdust that comes out, or the ejected that's cut out behind the drill bit, is very thick and curly, and it makes this a really perfect hole. So remember, ship auger, nice clean hole. So here's a demonstration of what the common grade cable would work. Again, remember I said that you can work this by hand. So here, this is the 7-strand. We're going to wrap the whole cable around the thimble so that we get our bend radius in place so that we won't kink it. We'll let this end off, 12 to 18 inches away. And this is the part that goes off to the other end of the branch, at the other end of the system. So we'll take, unwrap, this 18-inch piece. We'll take our first one and begin to wrap it around very neatly until it's completely wrapped on. Then we unroll the 6th strand and do that, and then the 5th, and then the 4th, and the 3rd, until we get them all on here, until we've used them all up. And notice how they're just laid one after the other. There's not big open gaps. There's not stuff hanging out. All that. So you want to make sure this is nice and smooth so that one, your climbing rope doesn't get stuck on it, or the climber doesn't get stuck on it, or the tree doesn't chafe on it. So you'll take a little pair of pliers and you'll make sure that this is rotated into place nice and smoothly, just like you see there. So the other type of cable is that aircraft cable, and that stuff you really can't unweave it to make an eye in it. Like this stuff, this we can produce, we can make this eye. With aircraft cable, you really can't do that. So you're still going to run that aircraft cable through a thimble, and that thimble is going to go through your piece of that you've installed into the tree. But then after you go around it, you're going to lay it parallel to the branch. Not to the branch. You're going to lay it parallel to the standing part of the cable, and you're going to attach these U-bolts onto it so that it pinches. So both pieces of cable, the short end and the working end, are both going to go through here, and you're going to pinch the cable onto itself about 3 times. The cable, so cable stops is another thing. These are metal knobs that are affixed to the steel cable ends protruding through a drilled hole. Yes, so they should not be used to form terminations on cables greater than 1/8 of an inch in diameter. So remember, this is going to be for fairly small diameter cable. You're not going to have a big giant cable here. All right, so now that we've talked about sort of how it's installed and what the materials are, let's talk about where to install it. So you want to install the cable at least 2/3 the distance from the defect, or where the weak crotch is, to the ends of the branch. So it's not 2/3 the height of the tree in a regular cable installation. It's 2/3 the height or the length of the branch from the point of origin, the defect's origin. So this is a pretty good example. So we have no idea how tall this tree is from here to here, but it doesn't matter to us. What matters is from this point all the way up to this point. So you want 2/3 of this distance, and that's where you want to install the cable. Any closer than 2/3, and you begin to transition the resulting forces back towards the crotch, and it can actually do more damage than good. The cable should be installed perpendicular to an imaginary line that bisects the union. So again, if we drew a line straight out that's halfway in between the 2 branches, we want our cable to be perpendicular to that. So it's 90 degrees off. Same thing here. Here's one that faces straight up. We want this to be 90 degrees off. So the angle from here to here is 90 degrees. So here's some real world examples. These again, these are lags, so these got screwed in. This looks like this cable, so you can see where that kind of wrap, that's that quick wrap that goes around, that dead end wrap that goes around the tree. It's important to have the cables pulled directly in line with the hardware, not at an angle. Notice the hardware is horizontal or perpendicular to the trunk of the tree in this case, and it comes flat out. Same thing up here, it's coming flat out. We want to avoid the scenario where the cable is pulling at an angle through the tree, because that's going to push it, it's going to create a downward force on this side and an upward force on this side, which over time is going to create more wounding. And it lessens the strength of the overall system. The cable, again, should be just tall. In other words, we don't want that big U shape. We also don't want it so tight that we can play a note on it. So it's just tall. So it's, that U shape just goes flat. Any more than that, you're going to put too much pressure on the hardware itself. The more pressure you put on the hardware, the more damage the hardware could cause to the living tissue of the tree. If the cable is installed while the tree is in foliage, it should be tight enough to compensate for leaf loss in the fall. I made this mistake early in my career and go and install this cable, think I did a great job, and then winter comes and all the weight comes off of the branches and the branches stand up, and my cable has this nice U in it again. So make sure that you're accounting for that kind of loading. Again, this takes practice and experience. You're not going to get it right the first time. And if you do, it's a miracle. So you have to install these things, go back and look at them over time, which is actually part of your responsibility. So we'll talk about that in a minute as well. So here's an example. This is just talking about the forces. Remember earlier I said that if you did not get 2/3 of the way up, then the resulting forces of the wind loading could be expressed down in the crotch itself, which is what we don't want to have happen. So if you put the cable too low, you're going to have this sort of inward pull, which actually is going to pull outward, or going to pull that base apart. If you're up high enough, then that's not going to happen. So at least 2/3 of the way up. So notice this is what we call a static cable installation. And this is what we call a dynamic cable installation. That's a little different from each other. We'll talk about those differences in a moment. We'll talk about now these sort of direct triangular and box connections on these multi-lead trees. Again, think about a Bradford pear that's got a bunch of leaves going straight up. And we want to try to hold all those together so that the tree moves in unison and not all this sort of chaotic motion, which can lead to early failure. So a direct is just one branch to the other. Triangular is where we're going to form a triangle. So this branch is supported by these two, and this one is also supported by these two. So here we have two triangular connections. Here's a box connection. So this just goes around to the outside, so they all kind of have to move together. This one might be used, it just depends on what the defect looks like as to which of these that you would use. And again, that's something you're going to gain in field experience. So just know that these types of connections exist out there. And then if you go and intern with somebody, maybe you'll have the opportunity to see them. So when we have these type of connections, we're looking straight down on top of this triangular attachment. So it looks like all these cables are right on the same plane with each other, but that's really not what we want to have happen. We want to have them be slightly different from each other because the hardware again goes all the way through the tree. So we're going to damage the cambium on this side of the tree. We're going to damage the cambium on this side of the tree. Same thing with this cable. We're going to create a little decay column going up and down there and a little decay column in the back. We don't want these decay columns to begin to touch each other. So to prevent that from happening, we want to, in 3 dimensions, we want to space these installations apart from each other. And so how far do we want these apart? The minimum should be greater than the diameter of the tree. So if this is a 10-inch tree, we want these two to be slightly more than 10 inches apart. so just more than 10 inches. If it's a 12-inch tree, we want these two to be 12 inches apart. Again, if you're putting multiple cables into a tree, we don't want the cables to cross over and touch each other. We want them to be far enough apart that given any weather conditions, they're not going to come into contact with each other. You also don't want, if you're attaching it here and you're attaching it here, you've got these two branches and there might be some branch in between them doing something funky. You don't want that branch to rub on the cable either and cause damage to the branch. Only one cable should be attached to any one anchor. I know that I was always tempted to do this because it makes sense in your brain, but structurally we don't want that to happen. So just one cable per eye. You don't want one cable going in this direction and one going in that direction. One cable per eye, the cable needs to pull in direct line with the cable. Anchors should not be installed into decayed areas where the amount of sound wood is less than 30% of the branch diameter. And this is kind of tricky, but sound wood is that portion of the xylem tissue that is not decayed in this situation. It does not include the bark. So if you're measuring to make this calculation, how big is this decay column or how big is this area of decay in comparison to the portion that's not decayed, do not take into account the bark. So if the bark is 2 inches thick and the whole piece is 12 inches, then that's going to leave you with a possible 10 inches of good clear xylem tissue. And from that, we would subtract whatever the decay area is. Again, these are areas, and we don't necessarily need to get into that on how to calculate this 30% loss, but just know that it does not, sound wood does not include bark diameter or the diameter that bark contributes. Much of the holding power comes from the wood, the callus tissue that develops after installation. So remember, we drill this hole and it's going to wound it. When we wound it, there's going to be what happens. We think about that coated model, right? So what's the fourth wall of the coated model? That's the new tissue that grows. That's everything that grows after the initial injury. So the more it grows, eventually it's going to grow around the hardware that you installed into the tree. Every year that it adds a layer of tissue around and over your hardware, the stronger that hardware becomes. Your hardware must be inspected annually. If you are a private tree care company and you're selling this to your client to reduce the liability associated with defect, then if you install that cable, you are taking on some liability for that cable. Is the cable still strong enough? Is it properly installed? Is the tree healthy enough to continue to support the cable job? In other words, is the tree not responding appropriately? Is it not growing new tissue? Then decay can set up on the inside. So every year you need to go back and take a look at it. Decay does not happen in a hurry. So annually is what's acceptable. If you cannot get your client to agree to allow you to come back annually, you need some type of release from that liability. So in your contract somewhere, you might say client has full responsibility for arranging the annual inspections. That way, if they don't call to arrange for the annual inspection, then they become the ones liable in theory. Cables may need to be installed higher as the tree grows. So, if you're putting cable systems into fairly young trees, those branches and leaders continue to grow. As they do so, you're going to have to go back every 5, 10, 7, 15 years, whatever the increment is, depending on how fast the tree grows, and install an additional set further up the tree. So that's all been, everything we've talked about up to this point is cabling. Now we're going to introduce the idea of bracing. So these are steel rods that are installed into the tree. We're not talking about rod or dead end hardware anymore. This is just a solid piece of rod that's going to connect between. It's going to help connect either through or in proximity to the defect. These are always used in conjunction with cables. You can install cable systems into the tree without installing a bracing system, but if you install a bracing system, it must always include cabling. And again, we have the two types of rods. We have the machine threaded rod and we have the lag threaded rod. Remember, lag thread means it needs to bite into the wood, so you're going to drill a slightly smaller hole than the diameter of the rod. Machine threads means that it needs to push through the hole, so the hole needs to be slightly larger than the diameter of the and it's still by the same amount. So here we're going to look at connecting two leads. This would be something you would do on a fairly small tree or some branches that you think might split apart. You can install this lag threaded rod. It's actually like just screwing the tree together. The rod itself, the threads on the rod are what provide the support. So the threads, as it goes through the material, is going to help either pull it together or keep it together. And you'll have to drill that hole slightly smaller than you would so that it bites into the machine threaded rods. Again, you're going to have a slightly larger hole so that you get it to go through. And that's going to be 1/16 to 1/8 inch larger than the rod. Machine threaded rods should be used in, this is what you're going to use in larger trees. Again, not the branches or small diameter leaders. This is going to be pretty big stuff that you'll use it in. A single rod should be installed above the crotch at a distance of about 1 to 2 times the branch diameter. So if our branch diameter is 10 inches, then you're going to want it 10 to 20 inches above the defect. Once you install this thing, remember this is a long rod, it might be 5 feet long, and the distance from here to here might only be 4 feet, so you're going to wind up cutting a little less than a foot off at the end of it once you cut those pieces off. You don't want the nut you don't want the nut to be able just to back off. So you're going to hit that thing, you're going to hit those threads with a hammer to bend those threads or collapse those threads against the adjacent thread. That way the bolt won't, you're going to basically mess up those threads so that the nut can't come off. That process is called a peen. So you're going to peen they're going to smack it with a hammer right here along those threads. So here's a homeowner attempt. This was, I was driving around and saw this and said, wow, there's a lot to learn from this picture. So a homeowner was given an estimate to install a bracing, cable and bracing. And he said, well, it's just phenomenally expensive. I'm not going to do that. So, this guy's kind of far enough away from the house where it really wasn't a hazard, but this is definitely a high risk for failure potential. Notice he used square washers over here. He did not use the round ones like we talked about. He left all of the ends on here after he finished. So he definitely didn't cut off the excess and peen it. The angle, if you notice, you got one angle that comes up, then it goes over, then it comes back down. So the system is not in line with each other. Remember, it's supposed to be a straight line going all the way through the tree. But he said, hey, I'm going to attach a turnbuckle here. It's going to loop through each of these eyes. I'm just going to twist and pull this thing together. So this is just a little J-hook here that was never bent over. There's no way to close that. So if the tree were to do this enough, then enough slack there to just make that come right off. So this is an example of absolutely what not to do. Violates almost everything we're trying to accomplish here. Okay, so we've talked about the static systems. So that cable is a fixed length. So if you have your two parts of the canopy that are sort of moving in unison, you're still going to get some movement that's going to want to pull it apart. And that's why it's there, is to prevent it from coming apart. But if the wind's pushing me in and then the wind cuts off, it's going to go pow. It's going to go to whatever the length of that cable is pung, pung, and it's over. So which can contribute a lot of force to the point of attachment on the trunk. So what they came up with is this sort of what we refer to as a dynamic cable, meaning that it can move. It's not static. It's slightly variable. This allows for a little more sway. It's not a bungee cord at all, but if you were to think about a bungee cord versus just a rope, if you jumped off a bridge wearing just a rope, and you get to the rope's end, and the rope's just going to go boom and stop you instantly and probably break your back or whatever. But if you jump off with a bungee cord, you're gonna reach the length of the cord, and then the cord's gonna stretches. It slows you down. It does not break your spine. Similar thing here, except instead of the rope stretching, the rope collapses. In this picture, you see this little faint spot right about here. Inside of there is this big rubber cylinder. It's called a snubber, and the snubber goes inside of this cable. This cable is it's woven fabric, and it's like a Chinese finger puzzle. So it's hollow in the middle. So if you push it together, it gets large in diameter. If you pull it apart, it gets small in diameter, just like a Chinese finger puzzle. So you compress this stuff, the hole gets large, you put the snubber inside of it, and then you pull it out. And the snubber holds it open about this big. So as the tree branches pull apart, it's like trying to pull on that Chinese finger puzzle. It gets tighter, and it compresses around that snubber, and it slows the spread. So it's not like not like a bungee cord where it could go feet, but this is just going to go inches, but it's going to slow it down so that it doesn't just pop. It's going to come out and slow down. It's probably the preferred system. It produces a lot less stress on the tree. It's adjustable, so you can go back every year, and if you need to take this out, move it higher in the canopy, you certainly can. It doesn't drill into the tree, so we're not doing any damage. However, the big problem here is probably the homeowner who doesn't want to pay for somebody to come back out every year to adjust it and inspect it. So over time, remember, we still have this secondary growth. So what's the problem with putting something around the trunk? That's right. So the tree would choke itself. So you eventually would kill the tree. If you never move this, you would kill the branch from this point upward. So you need to make sure that when these things are installed, that the homeowner is going to allow you to come back out and make adjustments. This stuff does degrade in sunlight, but it takes decades for it to do so. So the tree's going to grow in diameter before this stuff gives it up to photodegradation. So be very careful when installing these about being able to come back and inspect it. Remember, you guys can ask questions as we go along. Pop them in the question thing. We'll try to get you answered. So now we're going to talk about guying. So guying, remember, is from the tree to some external point. So this external point could be another tree. It could be a building. It could be a pole that's installed specifically for this reason. So just remember that guying is from the tree that you're trying to help to some external point. It does reduce tree movement. Guy wires should be attached to the tree at a point at or above midpoint or 2/3 the height of the tree. So if we have a 40-foot tree, this thing can be installed from 20 to some point above 20 feet. So the ground anchor should be placed no closer to the trunk than 2/3 the distance from the ground to the lowest point to the lowest attachment of the tree. So this is only when we're using what we refer to as a ground anchor. You've probably seen telephone poles that have a guy line that comes all the way down to the ground and attaches to something right at the ground. That's referred to as a ground anchor. So this distance away from the tree as you come up, like for a building or something like that, this becomes less important. So just sort of keep these ratios in mind for the test. Another way of supporting branches is by propping. Again, this is not used very much in the United States. It is very popular in other parts of the world. Propping is just what it sounds like. These are permanent, semi-permanent poles that are put in. There's a little cradle at the top, and the branch sits in that cradle. This one is sort of elaborate, and it helps so that when these branches move around in the wind, the pole moves around with it, and everything works in unison. It's kind of neat stuff to see in practice. There's a lot of respect that has to go for this tree by the passerbys. If this is a public tree, each one of these poles could produce a hazard to somebody under the tree. So this is probably why we don't see it very much in this country. All right, so that finishes the part on cabling and bracing. Next, we're going to move on lightning protection. I don't see any markers that are popping up in the question and answers section, so I guess we'll just go on to lightning protection. At the end of lightning protection.
The question is, Rob, when you were discussing dynamic support systems, you never called it the rope support system or referred to it as a rope. Is there a reason why it's not referred to as a rope?
It's really not a rope. It is sort of this hollow tubing that's like made out of seatbelt material, and so it's not a rope. It's tubular. So it's just this woven line.
Okay, awesome. Well, I hope that answered your question, Tony. And then Rob, if you could switch, I am seeing your notes screen.
Not this again.
Yeah, still seeing it.
I don't understand how the same.
Well, I didn't ever see that, normally it starts at the edit screen. I didn't ever see that one pop up.
You're still not.
Yeah, I'm still seeing the same thing. Whatever clicks you're doing, I'm not seeing that.
So what do you see now?
Yeah, I see your edit screen, so it should be the next click should do it. There you go.
That's the right one?
That's tree support and lightning protection. I think you removed.
I had to start over again.
Oh,
it's all the same presentation.
Oh, okay. I thought it was going to be a separate one. Okay.
All right.
Hey, cool.
Okay, back to it. So, we've talked about cabling and bracing and guying. So now we're going to talk about a slightly different entity, but it's sort of for the same thing. We're trying to mitigate some type of risk and trying to protect the tree. Lightning protection systems are not exactly what they sound like, but they accomplished that. So lightning is this very intense amount of electrical discharge, and it is so great that it's very difficult to control. However, there are mechanisms that we can use to keep it from doing significant damage to the tree. As you see this pine without a lightning protection system in it, you've seen this stripe going all the way down to the ground. Lightning may strike a tree, travel down the stem, then leave the tree, jumping to a more conductive tree, structure, person, or animal in a side flash. I like to think about a clothesline, something that, or some other type of metal object that's attached to a tree and attached somewhere to the ground. So the lightning is going to take the path of least resistance. So it's going to come down the tree to the point where it hits something that's more conductive. So like a clothesline, and then it's going to discharge down that clothesline in what's referred to as a side flash. Lightning exits a tree through, in the absence of all that sort of thing. Lightning exits a tree through the roots and dissipates into the soil or ground. So we think about grounding. That's where the potential energy is coming from the clouds, traveling through the tree and then dissipating into the ground. So whenever you have current, you have to have some voltage, and there has to be a potential difference between the poles or the circuit. So if you think about a battery, like a car battery, you have two posts that stick up, and car batteries are typically 12 volt, depending on where you live in the world. Ours are 12 volt batteries. So the potential difference between here and here is 12 volts. If we connect the two poles directly, we short out the battery, you get this big spark, much like lightning. However, if we put some circuitry in between, then we're going to change the voltage and the current that goes from this pole to this pole. As it flows, that's going to be current or amperage. So step voltage is a great difference in the electrical potential that occurs at the soil surface as the charge is dissipated. So here we have this car battery that, this pole and this pole are 12 volts, they're fixed. But if we were to dissipate this energy into the ground, well, we have our tree, and then for every distance you get away from the tree, you have a step down in voltage. So if the tree's all of a sudden 20 million volts due to the lightning strike, 1 foot away it might be 1,000,000 volts, or difference in voltage becomes like the car battery's 2 posts. So in between, if you were to connect the two, there's a difference, and you can develop current because there's a potential difference. Make another step out, and maybe now it's 500,000 volts. Another foot out, maybe you're down to a few thousand volts, and then another step out, you might be down to hundreds of volts, and then another step out, maybe close to nothing. So you can usually fully dissipate the energy into the ground in about a 10-foot diameter cylinder down into the soil. So that's if you can imagine that cylinder with the center point being the tree or the ground rod or wherever it's dissipating into the soil, every step away from it, there's a slight change in that voltage. So wherever there's a change in voltage, you have a potential for current. So if you were, say standing there and you had your legs apart, the difference in voltage and you're the connection, well, that current's going to flow through you and it could kill you. Lightning protection systems in themselves are effective in reducing the risk of damage to the trees and their surroundings in the case of a strike. What trees are susceptible to a lightning strike? Well, it's the tallest tree in the group this is usually trees grown out in the open. If you have a tree all by itself out in the prairie, trees that border the woods or the line of street. So, anywhere where you sort of stand out as something tall, you're going to be more likely to be struck than those out in the middle of the forest. Trees close to water. So again, if you have a lake, the edges of a lake are very similar to the edge of a street or a highway. Trees on top of a hill. If you get on top of a hill, then you could be the tallest tree around and get struck. Trees in local areas or geographic regions with a history of numerous lightning strikes. Contrary to popular belief, lightning does strike twice in the same place quite often. I know we have people from all over the country, but in metro Atlanta, we have this road that goes through the city called Mount Perrin. And Mount Perrin actually is on top of granite or basalt outcrop in a granite area. So you have this sort of vein of basalt that runs through the granite. And because of this dissimilar type over a large geographic area, Mount Perrin becomes sort of this lightning alley, and lightning strikes happen in that area quite frequently. So that would be an example of a geographic region that has this issue. Laser pointer. There we go. Another thing that can attract the lightning or make the tree more attractive as a grounding tool would be cables in the tree. So all those cables that we talked about earlier, those are going to add to the potential of a lightning strike. Which trees should be protected? Lightning systems are not cheap. They can be expensive to install, incredibly expensive. So on some of our great historic and landmark trees, I'm working with one now that's a very historic tree, and our estimates for the installation of lightning protection, all inclusive, is going to be close to $10,000. So this is not cheap undertaking. It can cost as little as maybe a few thousand for a pine tree with one central leader, but big spreading oak trees such as a live oak or something like these things can get very expensive. Large trees that are within 10 feet of a structure. So if you live in one of these areas geographically, it's always getting struck, you might want to protect your house or your structures as well as the tree. So putting these systems into the tree is a good idea. Trees where people seek refuge, like golf courses and parks. On the PGA, courses, if you ever go to play golf on a PGA course, you'll notice that at the tee boxes, there are quite frequently trees with lightning protection systems in them. This was originally installed to protect the camera crews and their equipment. So it's really not for you, it's to save money somewhere else. But other places are trees that stand alone. So if this is a high value tree to you and this tree stands out in the open, it might be a good subject for lightning protection system. So lightning, as I said earlier, is super intense, and we can't really run it through the wire like we do with the cables or the wiring, let's say in our house. Our 120 volt lines that we have inside of the house, they have a plastic sheath around the outside of them. They have some a ground wire included with it, stuff like that. But it's either a solid wire or it's a woven wire, tightly woven wire, and it conducts the electricity through the wire instead of on the outside of it. So what we use in lightning protection is this very loosely woven copper. And this is like super open. This is blown up a little bit. This would probably be a 1/4 inch diameter. So it's not really this big, or it could be a 1/2 inch, but no bigger than that. But it's loosely woven. And what happens with that loosely woven copper is that it guides the strike. So it doesn't really conduct the strike, but it travels as a halo around this woven copper. So you're going to use this as your ground, your main line. So the copper conductors that extend from the top of the tree down the main branches and trunk into the ground, and then you're going to ground it you're going to put in like a 10-foot long ground rod. All the hardware that you use in this lightning protection system should be approved by the National Fire Protection Association or Lightning Protection Institute. So it'll either have LPI on it or the National Fire Protection Association insignia on it, or the approval stamped in it, something like that. So remember that approved generally refers to hardware. The uppermost point of a lightning protection system is referred to as the air terminal. It's pictured right here. So this would be as high as you can get it into the tree, but it does not need to extend higher than the canopy of the tree itself. It's okay if it's just inside. It's going to be so much more attractive to lightning as a way to discharge into the ground than the canopy is, that it doesn't have to be all the way out. It's just the lightning's just going to come straight to that tip and go down the travel by that guide of copper wire. Air terminal should be located, however, near the tops of the branches, but does not have to extend beyond. That woven cable that you saw here is laid inside of these teeth, and then a pair of pliers are used to bend these teeth down and crimp the wire onto the device. So they use dissimilar metal types. So we have this brass or copper clad piece of point, which goes down and attaches to your copper. But then the base of all of this is brass. Brass is more resistant than copper. So the lightning, again, is going to want to travel the path of least resistance. So it's going to stay on the copper part. And then these nails would go into the trunk of the tree. This is what holds this thing up. So it's actually physically gets nailed into the tree using these little very expensive brass nails. So this little foot is what sits on the branch of the tree. And then there's a hole in it. You put the nail in it, nail it through. So that one that attaches to that main terminal, this is referred to as the main conductor. And we're going to hold that main conductor off of the trunk of the tree some. Remember, the lightning travels down it like a halo. So if it were against the trunk and it's traveling down it like a halo, it's going to burn the bark off all the way down. So we want to hold that cable some distance off of the trunk. So we use these little stanchions, and these stanchions are several inches long, and that's what's going to hold the cable away. So this part is about the same length as the stanchions, but instead of having a tip like that, it just has one open sort of U-shaped piece. You lay the cable in it, then you bend it closed. hold it. The secondary conductor also attaches every 3 feet. So secondary conductors might be on side branches. So you have your main conductor that's up at the tallest point of the tree, and then these leaders that you might have, these lower leaders in the tree that extend way out on the canopy. These are going to have secondary conductors and secondary terminals out at the end. You'll bring it together, attach it to the main conductor. The conductor should take into account the sway of the tree. And this can be kind of difficult to understand, but if you have a branch that's, say, here's the edge of a pair of glasses. So if I were to stand it off here and then stand it off here, and the cable sort of makes this rotation, if the wind blows and goes like that, the cable is going to come down and touch the part of the tree. So it's going to be up here, then come down. So you need to put these stanchions close enough together so that when the branches flex and move, that as it flexes, that the cable's not getting closer to the trunk or touching the trunk. So 3 feet, these 3 feet intervals are a guideline. You don't want it more than 3 feet apart. It can be less than 3 feet, but not more. And you say, well, why don't you just go ahead and put them 2 feet away? Well, these things are brass and copper, super expensive now, so that it adds tremendously to the cost. A ground terminal is installed to provide electrical contact with the ground. Remember, we have that step voltage, and we want to discharge that into the soil. We don't want to discharge it into the tree. So we want to get it some distance away so that our discharge area is not going to damage the tree either. You also want to make sure that that discharge column is not close to the electric lines of your irrigation system, or to the main line of the house, or to any type of metal conductors that are in the ground, whether it's your cable for your internet or whatever, or your phone lines. Nothing that can conduct should be inside of that 10-foot dissipation cylinder. Blow up everything in your house. Ground conductors, or the plate, and we'll talk about a plate in just a second, associated with the connectors. 2 or more trees with protection systems should be connected if they are within proximity to each other. There's what's called balancing the system. So we want all of these, if there's several trees in an area, like say at the top of the hill, and you're putting in multiple trees, you're going to want to connect. They're each going to have a separate ground rod, but you're going to want to connect those ground rods to each other so that it balances out. So the conductor cable should come off of the tree trunk and be buried 8 to 10 inches below the soil and then grounded. So here's our cable. So we're going to put it just under the soil. And to keep from damaging roots, you might want to use an air spade or some type of air tool to open up a trench and lay the line in so that you're not cutting roots, and then cover it back up. The ground rod must be driven into the ground 10 feet, and the cable should be forked in rocky or sandy soils. I'll explain that in just a second. So you want to be 10 feet or greater away from the trunk. The bigger the tree, the further away you want it. So we talked a little about the zone of rapid taper earlier. I like for these ground rods to be well outside of that area of rapid taper. So the bigger the tree, the further away from the trunk that's going. The old standard was to come all the way out to the drip line and place it way out of the drip line, but they decided that it doesn't have to be that far away. And you want the total amount of dissipation area to equal a 10-foot ground rod in depth. So if you can only go down 5 feet and you hit a rock, well, you cut it off, and then you move some distance away, sink the other 5 feet, and then connect the 2 ground rods so that you still have that 10, what's equivalent to the same soil volume as you would have before. So that's what it means by rocky soil. You might want to divert those, so you'll have to fork it. So you might put a fork in the line way back here, so it might not be connected directly to this ground rod. But this ground rod, you might just fork the system and run one over there, one over to here. But they're connected on the same down conductor. We talked about plates just a second ago. So a plate, if you have a really rocky area, it's all rock and you have no soil. For those that live around Metro Atlanta, if you ever go up to the top of Stone Mountain and look at the towers on top of Stone Mountain, you will see that they have the woven down conductors on the towers, and then they go over to these big plates, and the plate does the same thing. So it's just sort of this huge plate, and they have it fenced off so that you can't be standing on the plate when lightning strikes. You really can't get to them, but you can see them. So you can see what these plates look like. So these are just bolted directly into the granite surface of Stone Mountain. It's kind of interesting to see the different ways of grounding these things out. So here on this tree, this is telling us quite a bit. You can see these little stanchions about every 3 feet here as it comes down the trunk of the tree. Here is a cable system. And we want to tie the cable system in. So in case the lightning hits the cable system, instead of discharging in the 2 ends, it's going to want to go through our point of attachment and go again to our down conductor and to the ground. This would be our main conductor. This one would be a secondary conductor, so a secondary terminal, and the primary or main terminal at the top. As the tree grows, so if you're installing this in a young tree, you're going to want to move those air terminals up every so many years so that it continues to be closer to the edge of the canopy. Lightning protection systems, again, should be inspected annually and maintained as necessary. You know, the PGA in their great wisdom decided that we're going to put in some protection around all these tee boxes, but they never made an allowance there for the maintenance of these lightning protection systems. So quite often, if you're on a PGA course and you go around and look at these lightning protection systems, you'll notice that they're in a state of disrepair. This was something that they put in the PGA, I think in the early 90s. And so no one's really touched these things since the 90s. So again, the tree is going to grow in secondary development. So it's going to get bigger and bigger. Remember those stanchions that we put in the tree that used to be 3 inches? So after a few years, it might only be a ½ an inch. More years after that, it can be totally touching the line. By that point, the lightning protection system is not going to help you anymore. You're still going to get that burn. So it needs to be adjusted every few years to make sure that it's staying off the trunk of the tree and that the air terminals are getting moved out to the tips every so many years to make sure that the system's still going to function for its original intended purpose. All right, so that's it for the lightning protection section. Again, if you have questions, I'm always happy to help answer those questions. I encourage people to take on mentors here so they can help explain these things to you.
While Rob's getting that set up, does anybody have any questions?
All right, do we have the right screen up?
So far, I can't see anything.
So just black?
Just you.
Just me.
Just your face. All right, perfect.
There we have it. Okay.
Got it.
All right, so we had our break a little earlier, so we're just going to go ahead and jump into the plant healthcare section. Again, if you have questions, feel free to send me an email. Plant healthcare. This is a very interesting topic, very dear to me, because this is a lot of what I do in my practice is plant healthcare. So plant healthcare is really a holistic approach to mitigating disease and insect pressure. Compare that to what we used to refer to it as integrated pest management, or IPM. We'll talk about those differences throughout this chapter. It's important to know what defines a healthy tree. I've said many times that you have to know how trees should be in order to know when they're not right. So work on that. I hope you've all thought about the sort of 10 by 10 spreadsheet that I spoke about earlier. If you'd like a copy, we can provide a copy of that for you. That's sort of one that you can use to see how it works. But knowing how a tree should be is the most important part of the whole deal here. We're going to talk about the appropriate response process, the ARP. We'll talk about the allocation of plant resources and how that affects plant health, monitoring programs, pest management options, and preventative strategies. What is plant health care? It's a holistic and comprehensive program to manage the health, structure, and appearance of plants in the landscape. What does it do for us? It helps us to tremendously reduce the use of broad spectrum pesticides. Remember, whenever you see the word pesticide, that is an all-encompassing term. Herbicides, insecticides, miticides, rodenticides, all of these are pesticides. So when we say pesticides, that's the largest term that we can possibly use. We're going to manage the cultural practices of the landscape, and by doing so, we can impact the health, growth, and development of turf, shrubs, trees, and other plants that we might have. PHC, or plant health care, ideally begins with the design of the landscape and selection of plants, putting the right plant in the right place. I know that we have lots of clients now that want these kind of exotic plants that are marginally would grow in your specific area. And as a result of being marginal, they're going to have that constant stress. Remember, we talked about chronic and acute stress. Chronic stress is usually environmental. So we want to have the right environment for the right plant. So what makes a healthy plant? A plant is considered healthy when it's free of disorders and pests and has sufficient ability to resist stress. Remember, a nice normal tree doing its thing out in the forest, if it's not a suppressed tree, it's going to produce about 66% more energy than it uses. So it's going to store all that stuff, but that's plenty of energy for self-defense and reproduction and protection and fruit, all that sort of stuff. So it's all going to be there. That's a healthy plant. Let's talk a little about vitality and vigor. Vitality, this is an individual plant that we're talking about. A plant's ability to deal effectively with stress and thrive in its given environment. So if I have a cedar elm in central Texas where I am, that cedar elm is going to do pretty well here on the edge of the prairie. However, if I take a Japanese maple and try to plant it out here, it's not going to do very well. So vigor has to do with, this is a species level thing, a plant's inherent genetic capacity to resist stress. So a dogwood has plenty of vigor, but because I've taken an individual dogwood and planted it in central Texas, it's going to have very poor vitality. So we want to have vigor and vitality. So I might take my dogwood and plant it in a more temperate area. It has a seasonality. I might plant it in some shade where it has everything that the plant needs in order to express vigor. Hopefully that makes some sense for you. Some things that can impact vigor might be environmental stresses, insect and disease resistance.
Hey, Rob, Rochelle has a question. This may not be able to be answered right this second, but she says she's never heard that 66% extra energy production. Is there a way we can get her a research citation on this so she can read up on it?
Yeah, I think that original research was done by Dr. Alex Shigo. So if you do if you read Touch Trees or a few of the other Shigo books, you can find that information there. Dr. Ed Gilman in Florida and Dr. Kim Coder in the University of Georgia all have done similar studies to come up with the amount of photosynthate that's produced and how it's allocated.
Okay.
So you might try some of those.
All right. Rochelle, sorry. I will do a quick Google search and just drop anything I find there in the chat for you.
So the University of Georgia has a really good system there at the Warnell School of Forestry. And you can get access to Dr. Coder's materials on that website. He covers a lot of topics, a lot of research stuff. And as he produces that, he does make it available to the public. So that might be a good place to take a look. So I was talking about environmental stresses, insect and disease resistance. If plant's in the right place and is treated properly and has all of its mechanisms, something as simple as this, where the caterpillars are munching away on the leaf, Those trees can produce signaling chemicals that they can actually send through the mycorrhizal connections to tell the other trees around it that, hey, I'm under attack. And they can produce more tannic acid, more tannins that they can push out into the leaf to make the leaf taste bad. And that can help resist decay. So the sort of benefit of having the right tree in the right spot. If I have a tree that's isolated from all the other ones, that communication network wouldn't be there. And the trees likely, and those around it, would likely get defoliated. Now let's talk about this resource allocation. It's not just about the color and the growth rate of the tree. It's not, do we have a fast growing tree? Do we have a dark green tree? We need to take everything into account. 4 primary functions of resource allocation by the tree are maintenance and reproduction, growth, storage, and defense. Reproduction is a huge energy loss for the tree. I mean, think about, a handful of walnuts has a tremendous number of calories in it. And so, I mean, it's a good nutrient source for us, but the tree doesn't get really much of that back. It's carried off by other animals, and it's a loss of energy that it does in hopes that, it's going to have offspring and continue on into the future. This is the same reason reproduction, it's the same reason that we would all reproduce, is to make sure that the future generations survive. So this is a big loss of energy. So you have to be pretty healthy in order to do reproduction. Growth, you have the primary and the secondary growth. We have storage. Again, if we have a nice healthy tree, we're going to be producing a lot more energy than we're consuming, and all that's going to get stored away. And so we have this storage area. Defense, again, we might want to be able to produce those tannins in the leaf to make the leaf taste bad. We might want to grow thorns. We might want to make a thicker leaf. We might want to grow thicker bark. All these sorts of things require energy that doesn't give back to the system. So in a healthy tree, it's gonna be pretty easy to keep all of these things satiated. We've got the right amount of growth. We're not growing too much. Like if you over fertilize the tree, you're going to be putting more energy into tip elongation and producing more xylem tissue, all this sort of thing. So we might throw it out of balance by over fertilization. We might cut off a bunch of the root system, which would impact our storage. How much we can store, because we might be just trying to regrow root system at the expense of reproduction, or at the expense of defense, or the expense of growth. After construction, if you look at the internodal growth, it'll probably get smaller and smaller for a few years, and then it'll get bigger and bigger. So in a fairly balanced system, that's what we want to see. We don't want to see it get a little smaller and smaller and smaller and smaller until we finally have no growth at all. In resource allocation, it varies by season, environmental conditions, and genetic strategies. An example of a genetic strategy, we talked a little about compartmentalization of decay in trees. Every species does not have the same effectiveness at isolating decay as each other. So like a tulip poplar and a post oak. A post oak is a very good compartmentalizer. It's a slow growing tree. It has lots of fibrous tissue. It puts in tyloses and all of the old xylem tissue that plugs it up to keep things from spreading. Compare that to a tulip poplar that just grows like a weed. It grows crazy fast. So its defense mechanism is to outgrow decay. Whereas the defense mechanism for a post oak might be to isolate decay. Isolating decay takes a whole different set of chemicals than fast growth does. So that is a genetic difference between the two species that has a direct correlation to how it expends or allocates resources. Seasonality, obviously deciduous trees are going to put a lot of effort into manufacturing new leaves, into tip elongation and vascular development in the spring. Then in the summer, it's going to slow down. It's the consumption's not going to be as great. In the fall, it's going to switch again to maybe trying to reabsorb some of those chemicals and store them away for next year. So there is some seasonality. Environmental conditions, right now here in Central Texas, we're under an extreme drought condition. And because of this extreme drought, the root system's not really doing a whole lot. the soils themselves are so hot that a lot of the bacteria, the beneficial bacteria, have been killed off in the soil. And so there's really not a lot of root system left. That small fibrous root system to soak up water. So the tree kind of shuts down right now. As temperatures drop and the rainfall begins this fall, everything will grow some new roots, and the bacteria will come back and start to repopulate. So that's an environmental stressor. Flooding can be an environmental stressor. Insect damage can be an environmental stressor. Mild stresses can redirect resource allocation, increase drought or pest tolerance. So as long as it's within, the bell curve, again, trees do best right here in the middle, but they can survive out towards the ends. But once you get past into the outlier areas, that's where trees really start dying. So what are some of the physical deterrents for plant defense mechanisms? So we have thorns, spikes, hairs, thick cuticles, a lot of cellulose or a lot of lignin to make things tougher. Cellulose and lignin are a cellular defense mechanism. So actually around the cell itself, this is what makes it difficult to get to the contents of the cell, would be the cellulose and the lignin. Trees, yeah.
I'm so sorry. I was trying to pop in before you swap slides. I don't know if you need to go back, but Danielle wants to know if you could also give an example of storage in a tree.
Yeah, so if you remember back to the biology section when we talked about those ray cells and the apoplasm, or the living part of the xylem tissue, but it's not conductive up and down the tree. The ray cells sort of connected across the growth increments. And so as extra photosynthate is manufactured, it comes back down down the phloem and moves from the phloem into the xylem through the ray cells. And so it just continually is storing or retrieving starches. So that's the storage area, is that apoplasm in the trunk. And it goes down into the root system and out into the branches and the twigs. I mean, anywhere there's xylem tissue, it can store it. Hopefully that answers her question. Any others?
That's all I got for right now.
Okay. So as we talked a little about earlier with the jugglins on the walnut, these compounds are referred to as alleochemicals. Tannins and phenols are alleochemicals. So tannins make things taste bad. Phenols resist fungal infections and other decay organisms. Chemical deterrents, these can be chemical deterrents to herbivores and pathogens. Some of our insecticides are actually concentrated versions of what trees can produce on their own. Nicotine is one of our most powerful insecticides on the market. It's funny that the things that we use to kill things, we also smoke ourselves. So nicotine or neonicotinoids are extremely effective insecticides. Pyrethrins, protanones, neem, these are all naturally occurring insecticides that we can either synthetically produce or the plants themselves can produce on their own as an alleochemical. Most insects are host specific. There are some aphids out there that will pretty much go over any kind of tree, but there's also some aphids that are specific to particular varieties of trees. There are beetles that like the emerald ash beetle really likes the ash tree. It might go after another tree or two, but it really likes the ash tree. The two-line chestnut borer really likes a chestnut, but it says, hey, not enough chestnuts. I think I'm going to go attack some weak oak trees. It can certainly do that, but it's really not, they're fairly host specific. Dutch elm disease is specific to elm trees and the group of the family of elms. Rapidly growing trees are sometimes less resistant to certain insects and diseases, where photosynthate is diverted from defense into growth. So again, Paulownia is a really good example, a tree that grows super fast. So instead of producing phenols and tannins and that sort of thing, it just says, to heck with it, if you eat my leaf off, I'll just grow a new leaf. If I break a branch off, I'll just grow a new branch. That's its defense mechanism, and that's how it might allocate its resources differently. So now we're going to talk about some of the reactions to the limitations or the biological defenses that we might see. So in the event that you have a limited supply of water, the stomates are going to begin to close as drought conditions approach or high temperatures approach, and you don't want to lose what moisture you do have. The tree is going to want to close down those stomates. The next thing that might happen is the cells begin to lose turgor pressure, so you might wilt a little bit. The leaf might not have its nice turgid appearance. It might look a little folded down. Another sort of bigger thing, if this is a more chronic issue, you might see an increase in root development. Only makes sense, right? So if you need more moisture, I'm not going to spend energy on growing leaves. I'm going to spend energy on growing roots, because the roots are where I'm going to increase my absorptive area and hopefully find some water. Eventually, you might have leaf drop. Now, there are some trees that are more archaic as far as the historic timeline of these trees. Things like poplars and river birch, trees like that, their reaction could be leaf drop as a way to stop losing moisture. And that's a naturally occurring defense mechanism. It's not like if your dogwood started losing leaves or your oak tree started losing leaves as a result of limited water. So that's a really bad sign. That means your tree's getting close to death. But a tulip poplar or river birch, that's just part of its normal defense mechanism. So again, it's important to know what plant material that you're working with, what it's supposed to do to know when it's wrong. Now, you could also have limited light levels. Again, I talked the other day about these sort of urban valleys, these urban valleys. So you've got, trees planted in between very high buildings. And an oak tree might like sunlight all day long, but if you put it in one of these little urban valleys, it might only get sunlight for direct sunlight for 2 or 3 hours a day, which is not enough. So what do you think it's going to want to do? If it's getting plenty of stuff out of the soil, but its limitation is light, what's it going to try to do? It's going to try to grow taller. It's going to try to make its leaf surface area larger so that it captures more sunlight. So the leaves that it does have, it's going to make bigger. And then the shoot growth at the top is going to be more excessive, because it says, well, the light should be up there somewhere. I'm being drawn to it for 2 or 3 hours a day. Maybe if I get a little higher, I can get 3 to 4 hours a day out of it. So you get that extra growth. In the event that you have nitrogen deficiency, you're going to get decreased shoot growth. So again, remember those internodal distances. So if those internodal distances are constantly getting shorter, one of the reasons might be a nitrogen deficiency. That's not the only thing that can make that internodal distance shorter, but in the absence of all other things, or you can do a soil test and find out. But nitrogen is a very difficult thing to test out of the soil, because it doesn't persist in the soil for very long. But if you're constantly interrupting the nutrient recycling, you're not getting nitrogen back into the soil. Parking lot islands is a good example. There's not enough organic matter usually in those parking lot islands to get sufficient nitrogen, so you'd have to supplement it somehow. But if you don't, then you're going to get decreased shoot growth. That internodal distance gets smaller and smaller. Again, nitrogen should come through the root system, so the root system is going to grow. It's going to become larger and more dense, trying to find that soil moisture and the nitrogen source. Another thing that it's going to do is the leaf size itself is going to get smaller, because it doesn't have the basic building blocks that it needs to grow a larger leaf. The leaves will become a bit thicker, so smaller and thicker leaves in the event of nitrogen deficiency. So you can have all of these things. The urban valley that I talked about is a great example, because it is sort of a parking lot cutout. You might not even be irrigated, so you're going to have limited water, you have limited light, and a nitrogen deficiency. These multiple stresses, especially in the chronic state, cause a state of decline, where the trees, that growth increments getting shorter and shorter every year. And eventually it could precipitate the mortality spiral. Once a tree enters this mortality spiral, there's really nothing you can do about it. You might as well take it out and replace it with something else, because once you get to that point, the options for reversing the effects are quite limited. So we have a process involved in plant healthcare. It starts with monitoring. It's a process of observing, identifying, and recording and analyzing both plants and their surrounding landscape. This will allow early detection and adjustment so that you can create an action threshold. We generally focus on key plants and key stressors. Plants with known issues for an area, such as lace bugs on azaleas. This is a known stressor. Plants of a particular interest to the client. You might have a specimen oak tree and they planted it in memory of somebody, or the species is very dear to that client's heart. So that would become one of my key plants that I would look for. So when we go out as practitioners, it requires a lot of feedback with the client. So it's not just about what you, the practitioner, might see as a problem. It's how that problem is perceived by the landowner. And that combination is going to what helps to set the appropriate response process and the action thresholds. So we're going to gather information, assess the severity and implications of the problem, determine the client expectations, and decide on a course of action. Avoid short-term treatments at the expense of long-term solutions. If you have a chronic dry soil problem, the long-term solution might be irrigation, install irrigation. Every situation is different. You can't just have a blanket answer that's going to take care of it. Remember, plant healthcare is about reducing the outside influences with pesticides. So to do that, we want to treat it. We don't want to use blanket treatments. We don't want to go out there and just spray everything on the property at the time of year when we think a few aphids might be around. We don't want to treat every plant because we're going to kill a lot of the good insects along with the bad insects. Again, the appropriate response process. Here's a little diagram for us. Client expectations is really what it's all about. What is the client expecting to get out of the program? How do they perceive it? A lot of the things that we do in plant healthcare, if we're doing our jobs properly, you won't see them. The client just sees a happy place. The plants are happy, everything's growing, everything's green. And that's primarily what it is that they care about. So if you're doing your job, you're giving them what they want. But of course, if you start giving what they want, they start saying, well, I don't think you're doing anything. And then they drop you and as a client, as a provider, and then a few years later, everything looks bad again, and they hire you back, and you go back and get it back up to the way it should be. That was poor perception with the client. Perceptions need to be established during this response process. You should communicate constantly with the client. If you're going out there 4 times a year, you should be communicating with that client probably 8 times a year. I'm coming out to take a look. You go out, you look, and then you recontact them. This is what we found. This is what you can expect to see. This is the way we've worded this contract. We're going to come out and treat 3 times a year in response to what we see, or in response to what we picked out as our key plant material. And so you just keep telling them that you're coming out and what you're doing and what they can expect as a result. We need to think about the plant material as part of this response process. Again, we know that about the vitality and vigor. Do we have the right plant in the right spot? Even if we have those things, we can still get lace bugs on our azaleas. We can get leaf miners on the boxwoods, things like that. On top of, don't always think of plant healthcare as just being a chemical thing. It's not just about plant observation. It's not just about the use of pesticides. It's also about pruning. Is structural integrity there? Can we prune to increase sunlight penetration? There's lots of reasons to think about pruning the plants. What are the stressors? What are the common stressors? So one common stressor for the azalea might be the lace bug. Another common stressor might be drought conditions that come about every few years. What's the potential of that stressor to actually affect the appearance, structure, and vitality of the plant? We want to address those issues. And when does it become significant enough for an intervention? Through evaluation, we're going to look for those signs and symptoms or specific events that are going to trigger these stressors to cause a problem that the client's not going to like. So we need to know when to react, when to actually respond to something. And we need to agree on that response as the practitioner and the client. So again, client education is absolutely essential. Also, there's a big difference between an aesthetic problem and a health problem. If you have leaf spot on your maple tree, well, it's really just the tree doesn't look so good because it has some leaf spot on it. Is 1 year of leaf spot going to be a big problem? No, not at all. It's purely cosmetic. If we had severe leaf spot year after year after year, probably because the tree is planted in a very humid spot in the yard, so it's kind of the wrong tree in the wrong place, it's going to develop this chronic problem, and then it turns into a health issue. But typically, that's not going to be, that would just be aesthetic. However, you take a red tip photinia and you have that same kind of leaf spot on the red tip photinia, and that will kill the plant. And it doesn't go away. So you have to intervene with a preventative program. So I would go out in that key plant material and say, look, you have this hedgerow of photinia, let's set it up on a fungicide application program, or think about replacing them, or a combination of the two. We want to minimize the use of broad spectrum insecticides, because every time we use these sort of blanket applications, you lose, like I said, our friendly insects. And you also risk pest resurgence. Mite control is a big one. A lot of people do these mite tests and they say, wow, we're just loaded with mites. But most mites are good, but some of them are bad. But a miticide is going to kill all the mites, the good ones and the bad ones. So using a mite-specific miticide might not impact the other type of insect, the beetle, and that sort of ilk. You're just going to affect mites if it's specific. So in that respect, it's good. But if you have a serious mite problem and you're using miticides only, then you're going to wipe out the good ones and the bad ones. Well, guess what? The bad ones reproduce much quicker than the good ones do. So think about, raptors and mice. Raptors don't reproduce at the same rate that mice reproduce. So if you wiped out all the raptors and the mice are going to come back much faster than the raptors will. So same sort of deal with pest resurgence. Secondary pest outbreaks. These can happen. A great example is boxwood leaf miner. We found out that the neonicotinoid application of merit, or when we apply that it does an excellent job of controlling leaf miner. However, we get a surge of a secondary pest, a mite that gets leaf. So that's an example of a secondary. So we took care of the primary, but in doing so, it developed a secondary pest problem. Integrated pest management is a little different than plant health care. IPM is the use of cultural, mechanical, biological, and chemical controls, which sounds a little bit similar, but it was really developed for row crop industry. So if I want to do a cost benefit analysis for crop loss versus the treatment expense. So if I have 1,000 acres and if I'm doing a monitoring program and I find out that I have a small little piece of land over here that has pest on it, then I go and apply the pesticide in that small area. Well, I've reduced the amount of pesticide. I did not wait for it to take over the whole crop area. The use of pesticides can be expensive, especially if we're talking about thousands of acres. The cost of the pesticides is not cheap. And so there's some, I have some value at 10 acres here, but if I go out and treat 12 acres or 15 acres of property, that's going to be less than just losing that 12 acres. In other words, I'm going to spend more money treating it than that 12 acres would have generated back to my whole income. So it's not time to treat yet. But if it gets up to 15 acres, well, now all of a sudden the crop that I save in there outweighs the expense of the treatment. It does also minimize adverse ecological impacts, because you're not spraying 10,000 acres, you're spraying 10 or 15 acres. So your impact on the environment is much smaller. Injury tolerance can be influenced by the plant's phenology. Phenology is about when something occurs in the annual cycle. So it would be appropriate, on a phenological circle, you have growth elongation in the spring. You have storage in the fall. You have somewhat dormancy in the winter, that sort of things. Those are all phenological events. Pest development may be affected by climate, like climate changes. We can use what's referred to as a degree day model. This is another one of those concepts that would be to your benefit to go outside of the material that's presented from the ISA and go work with this growth degree day information on its own to really get a grasp of how it works. But in some places in the country, growth degree day models are extremely effective everywhere. What these mean is that you're going to change the stage of an insect depending on the accumulated warming and sunlight periods that occur throughout the year. So it's some accumulated amount of warming an egg might hatch on day 73, growth degree day 73. But growth degree day 1100 might be when it's reached emergent stage and it's going to come out and it's going to start chewing on leaves. So I would know that at some point before that, I need to go out and make a pesticide application, low dose insecticide that's going to kill whatever it is that's going to come out and chew on the leaves, rather than waiting till the actual emergence day, when by the time I get out there to treat it, these things are much bigger and I'd have to use a much higher level of concentration of pesticide to get it. And so, not only does it help to reduce the toxicity of the pesticides that you're using, but it's also environmentally toxic, but it also reduces, or it can help you in planning. So you can plan when you're going to make these applications and explain to your clients that applications are going to happen between this date. This stuff worked when I worked out in Colorado. It was amazing. I worked with with Steve Geist out there, who's one of the great leaders. And he can tell me, he goes, yeah, Rob, tomorrow the leaf hoppers are going to start, or something like that. And it was amazing that he can have it almost down to the hour. It made their plant health care program very effective. Focus on prevention strategies and pest avoidance. Again, it's easier to prevent things from happening than it is to correct problems. Suppress pest populations to reduce levels and injury to a tolerable level. In other words, I like to think about it like a row of trees or a hedgerow of something. You might have mites on 2 or 3 trees out of 100. So if you were to go out there and use a miticide on the 2 or 3 trees impacted, and then 2 or 3 trees on either side of them, this allows the regular population, the managed populations of good and bad mites to stay in check. And so even though locally you killed both good and bad mites, they can come back in from the adjacent trees and repopulate the trees where we use the insecticide. And so you get back to this tolerable level much, much faster than you would if you just treated every tree in the hedgerow. If you have species of trees that are just prone to problems, such as fire blight, some of the common apple trees and things like that get fire blight, replace them with a type that is naturally resistant. That way you're not having to use pesticides out in the environment. Good sanitation. We have oak wilt here in central Texas, oak wilt's out in California and some other places. So by using sanitary pruning tools, where we're treating the tools between every cut, we're reducing the reinfection. So good sanitation, we're carrying away the plant material and getting rid of it off site. Here we have specialized dump sites where we can get rid of oak wilt so that we're not transferring it around, so it doesn't get turned into firewood and wind up adjacent to someone else's red oak in their yard with an active fungal mat reinfecting everybody else's trees. So good sanitation is important. Avoid overhead irrigation. Most fungi are mobile in water. So if you have a wet leaf and you're getting this leaf wet, you've got some fungal leaf spots here and they're producing spores. Those spores are going to get into the water, run down the edge of the leaf, down the stem, and then maybe drip onto some uninfected leaves below it that are now going to become infected. And this happens with overhead irrigation. Proper mulching helps to retain that natural nutrient recycling, because you're putting this carbon source on the soil that's going to slowly break down under the plant material. So we'll still have this nice, neat looking appearance, but now we've mulched it so we haven't interrupted the carbon sources. Irrigation for where we need it. And then we also want to avoid monocultures. You know, we've had all of our, a lot of trees been wiped out by the planting of monocultures, and the American chestnuts that were planted all down the streets of eastern shores of America. Once we got the chestnut blight, it came through and basically killed all the chestnuts. Dutch elm disease has killed a lot of elm trees. The emerald ash borer has killed a lot of ash trees. And it can just go from tree to tree to tree because we've planted these monocultures. So species diversity is super important. Most modern tree ordinances now take this into account and don't allow more than a certain percentage of any one species on a property. We can also have some biological controls, so we don't have to use chemicals. There's other things that we can use to augment the naturally occurring. So these things can take days or weeks to work, if they work at all. The three main types of natural enemies: we have predators, you know, like ladybugs. We had in North Georgia, they had the hemlock woolly adelgid, and there was a ladybug that liked to eat the woolly adelgid. And so it was pretty cool. They said, okay, well, we will release a lot of these things up in North Georgia. And so they released, or Carolinas, and they released a bajillion of these things around. And they went back to monitor how well they were doing their job, and they couldn't find any of them. Well, it turns out they were in northern Alabama and decided they liked Alabama better than they liked the Carolinas. So it's very interesting. They don't always stay where you put them. There's also parasites. There are naturally occurring wasps and nematodes and milky spore that we can apply to the bad guys that can kill them or do something to them to lower their population. We can also give them diseases to help kill them. And we can also use, we'll talk about some other parts of it. There's mechanical controls. You can physically go out there and pull a bagworm off and put it in a bucket of soapy water to kill it. So you're physically removing those bagworms. You can put in a physical barrier. The oak worms, we use this material that goes around the trunk of the tree, and when the worm crawls up the tree, it gets stuck in this physical barrier, like tanglefoot or sticky or something sticky or fat wrap. There's a bunch of different things out there, but it's a physical barrier to where the insect wants to go. Pruning also is a great mechanical control. If you have tent caterpillars, fall webworm, something like that, to get rid of them, you might have to prune out the branch rather than using an insecticide. You just reach up there and clip out the infected part. The same thing goes with fire blight. If you catch fire blight early enough and it's working out at the tips, you can go back from the fire blight, clip it out. You can prune out mistletoe, things like that. So for chemical controls, fungicides are best applied as a protectant. Fungicides are expensive, they're environmentally nasty, so you really want to reduce the use of fungicides the best that you can. However, if you've identified in your key plant material during your appropriate response process, you're going to identify maybe a tree or two that have to have fungicides applied. You can use fairly low dose fungicides as a preventative compared to, and there's no such thing as curative fungal problems on trees. And you're just going to manage those fungal disorders. So if you're using it as a preventative, you can use much lower concentrations. And so you're in effect going to use less fungicides by using them on a regular basis as a preventative than you would as a control. Some insects or insecticides can be broken down into a few different types. One is a contact pesticide, meaning that it actually has to touch the pest in order to kill. 7 or something like that. That's you have to dust onto the tree, and that dust has to physically get on the pest, or the pest has to walk across it or something like that in order to kill it. Another type is a systemic pesticide. This means that it's going to protect the plant from the inside out. So this is going to go either into the trunk or into the soil or sprayed on the foliage, but it's going to go into the vascular tissue and be distributed throughout the tree through translocation. Target specific spraying is preferred to broadcast spraying. Again, spray where the problem is. Don't spray the whole hedgerow if you don't have to. Read and follow the labels. I'd be remiss if I didn't tell everyone this. Whenever you use a pesticide, it is important to read the complete labeling. ING. The complete labeling doesn't necessarily have to be on the bottle or in the box in which you purchase the product. You might have to go to the manufacturer's website, and you might even have to go to your state's website to look for pesticides that might be banned in your state. California and New York are prime examples. They might have totally different labels in those two states than they do in the rest of the country. So if you move from Georgia out to California to do plant health care, you can't take the same thought processes there and use them in California because it would be against the law in California. So make sure that you read the complete labeling of the product. There are miticides, bactericides, herbicides. Again, all these things are pesticides. In order to apply a pesticide, you must have a commercial pesticide applicator's license, and the company you work for must have a commercial pesticide approval for or contractor's license. So you have to have an applicator's license and a contractor's license in order to apply the product as a company. Now, a company only has to have one licensed applicator on staff, and then people can work for that approved applicator. But you have to have at least one full-time employee that has an applicator's license in addition to the contractor's license. To learn more about it, you can go to your state website. This is the Georgia pesticide exam website. It's listed here. I haven't checked it in a year or two, so it might have changed since these slides were produced, but every state will have their own pesticide division. So go and look up your state's information if you're interested in this. Pest resurgence, again, this may occur when plants rapidly rebound or insects rapidly rebound in the absence of the naturally occurring controls. So you treat for one thing, and then like the mites, the good mites and the bad mites, you're killing them all. The bad mites come back faster. That's the pest resurgence. The secondary pest outbreak, again, this goes back to that leaf miner that we talked about on the boxwood. So I treat for the leaf miner, and then the mites take over and do a lot of damage on the plant. Pest resistance, we haven't talked about this yet. This most commonly occurs in fungicides, but it can occur across all pesticides. Fungi are very adaptable. So if you don't get complete control over the fungi, if there's a few left that can still reproduce, then those that reproduce are probably going to be genetically superior to those that were killed by the fungicide. So if you apply the same fungicide every year, eventually you're going to come up with like a super fungi that can't be killed by that fungicide at all. So we have to use a different class of fungicide every year so that we are totally changing the product compounds so that we don't develop resistance to that fungicide. So that's called rotation. So you're going to rotate your pesticides to different active ingredients or modes of action, MOA, over time. So there's alternatives to pesticides, biorational controls such as insecticidal soaps. These, the earlier that you can get it on, the better they're going to work. So if you're treating for scale, if you're applying insecticidal soaps during the crawler stage, you're going to do a much better job of killing them than you are trying to put them on at a different time of the year. Insecticidal soaps are pretty good at killing things that are easy to kill, such as aphids and mealybugs and young spider mites. Horticultural oils, these things are basically suffocate the insects, so insects breathe through their bodies. So if you coat it in an oil, then that oil is going to seal it off from the oxygen that it needs, and so the thing suffocates to death. But oils also can act like a magnifier. It can keep the plant from respiring properly. It can get too hot, and so you might create a phytotoxic injury as a result of using horticultural oils in the summertime. Horticultural oils are often referred to as dormant oil. However, they make a lighter version of it that can be used in spring, summer, and fall. But these things, horticultural oils, do a good job of encapsulating eggs that are laid by scale and spider mites and things like that. So by suffocating those eggs, you do not ever get that emergence in the spring. There are botanical pesticides like neem, pyrethrin, and rodenones. And then we have insect growth regulators. This disrupts the molting process, trapping systems. You might just trap them inside of a bag or inside of a box or something. We might use these things for monitoring or creating sterile insects. So some of these growth regulators would sterilize them so they can never lay eggs. Disrupting the molting means because they go through and get larger and larger and larger, but they have to exit their old skin in order to become a bigger one. So these ones that disrupt the molting never trigger that skin to pop open. And so the insect or the critter inside of it just keeps bigger and bigger inside of the same size package until it crushes itself to death. Not very nice to think about. Then there's some microbial pesticides such as Bacillus thuringiensis. Again, so you're giving them a disease. All right. So that brings us to the end of this one. And again, if you have quick questions, feel free to email me directly.